consider if you were to watch planet Earth, as maybe like an alien would through, a time lapse over the last 10 years, what you would see is the physical world in which we're living being vaporized by information, by data. I mean, consider was once a flashlight that had, warehouses and manufacturing facilities and factories and, trucks with supply chains delivering them to some store that you could go and, pick them up and carry them home. Now it's just data. It's just information. It's just lines of code that you download from the internet. A thing that's been sort of digitized. Same thing with a GPS system. Retail environment used to do this. I give this presentation to a lot of foreign nationals, and they always give me this puzzled look when they see the NASCAR slide. But again, so NASCAR replaced their sideline judges with high-definition cameras and computer machine learning. And that's the world. I mean, this is where we're headed. We're moving everything into this virtual environment. So this is one technology that really demonstrates that the physical world is now essentially lines of code that we can share on the internet and then print and manufacture digitally. So 3D printer. So consider the world in which if I need a new case for my iPhone, you could send that to me not through the mail system, supply chain. You could just email me a file for that. And so 3D printing is moving really, really quickly. There's a ton of conversation topics we could dive into. So I'll mention, you probably noticed the graphic in the middle of the screen. So this was a team from 2009, so almost 6 years ago now, that looked at the way we build houses. And they noticed that we haven't really changed how we construct things. And so they now have imagined sort of a building-sized 3D printer that uses Adobe sand, cement, whatever the material is, and they can now fabricate. In this case, they've done a 3-bedroom home in about a day and a half. That's the quickest they've done it. In China, a company just demonstrated that they printed 10 fully functional residential homes in this compound in a single day. And so right now the challenges are around safety profile, but if you consider the implications of in disaster areas, following natural disaster, you literally stamp out short-term housing, and this will improve over time. And then this is in the Netherlands. There's a Dutch architect who by 2017 hopes to have fully 3D printed the first functional office building. So construction is very much already in this world. This is kind of a subtle picture, but I'm gonna tell this story. So the image all the way on the bottom on the right is a piece of fabric that's being developed at the Lawrence Livermore Research Laboratory. And so what's really cool about 3D printing is because of the design elements, because it layers material, you can actually manufacture things that are far more complex than any other method of creating something. You can create these interlocking weave patterns, and because it's just digital layering, it doesn't care how complex the object is. And so with this particular fabric, so with most fabrics, when you stretch something, it gets thinner and weaker as you stretch it. That's just how fabrics work. With this, it's designed with an interlocking weave pattern so that as you stretch it, it connects and actually gets thicker and stronger as you stretch it. And so they're looking at how they might use that for aerospace, for defense, but materials, etc. And so sort of the domain of how we design things gets really sort of disrupted and changed by the rise of this new technology area. So I'm going to show this. So this is, if you watch TED, you may have seen this. This was announced a few months ago. But basically what you're watching is a new type of 3D printing. So the raw material is a liquid resin. And what the nozzle is doing is it's releasing a certain amount of oxygen and light to create a photochemical reaction. Basically, it's growing this object from a pool of liquid material and growing it in real time. The reason I'm showing this is what you're seeing being developed or printed would take any of the sort of traditional 3D printers from the previous slide, and I say traditional from printers of the last 5 years, would take about 8 hours. This was printed in about 10 minutes. So we're seeing, what we're seeing are decades worth of innovations now happen every few months. It's just the speed at which this stuff is coming online is just unbelievable. So that we're seeing decades worth of development at an unbelievable rate. So the other question is, how are we going to make sense of all of this information? We're swimming in this avalanche of Atlantic Ocean data water. Is that useful if it's it's just noisy information? So I'll use the Watson project at IBM to sort of demonstrate what we're seeing happen in artificial intelligence and machine learning. And this is one that is, I would encourage you to sort of pay attention to in the news. You're probably seeing a lot of headlines around sort of the controversy around artificial intelligence. So IBM, every 10 years or so, they create a challenge for themselves in computer science. So 10 years ago, they said, can we build a computer system that would beat a world grandmaster in chess? And so this was at a time when experts were saying, chess is far too complex. There are far too many permutations in the way a game of chess is played. We're decades away from ever seeing a computer do that. For thousands of years, chess has been a way of measuring intelligence. So in 1997, they created a computer system called Deep Blue, and it beat a world grandmaster at the time, Garry Kasparov, in chess. It was a big development, fairly exciting. And so 10 years later, they said, okay, so chess was interesting, but can we build a system that can navigate an environment even more complex than chess? And so the environment they chose was natural language. So transferring information through language is one of the most complex environments, systems that humans use. The subtleties in language, the double meaning, sarcasm, metaphor, all of these devices. And so Jeopardy, as you know, is a game show, is full of these literary devices. So I'll play this clip. This will give you a sort of a sense of what the Watson system was able to do.
For 400.
Familiarity is said to breed this, from the Latin for despise. Watson.
What is contempt?
Correct.
Let's finish Magical Mouse Dirty Tour.
In 1939's cartoon The Pointer, this guy got a new, more pear-shaped body, and pupils were added to his eyes. Watson.
Who is Mickey?
Mickey Mouse, yes. Now the last clue. Even a broken one of these on your wall is right twice a day. Watson.
What is clock?
Clock is correct, and with that you move up to 23,440. 18,000.
So are there any Jeopardy nerds in the room that recognize this guy? Yeah. So these guys.
So Brad's actually won more money.
Did he?
Yeah, well, over his career. Yeah.
Really? So Ken Jennings is this Cal Ripken of this unbreakable record of consecutive Jeopardy wins. He won more money?
Yeah, he's won. He hasn't had as many consecutive wins, but he's won more overall prize money.
Wow, I'd rather be that guy.
Yeah.
he gets write books about it, I guess. So I mean, so just consider that these two guys are not just some random Jeopardy players. These are the two best brains that humanity has ever created at playing this game show. And this computer system just beat their combined score by some absurd amount. And this is one of those examples where it's hard to have the perspective and to maybe perceive the significance of a development as we're living through these breakthroughs.
But it was bizarre that it said this is right twice a day, and his clock, but then his Watson's secondary guesses were car and nail.
So that's
so weird.
That's such a great point. So let's talk about that. So the way the Watson system works is a completely new type of system in computer science. So it used to be true in computer science that a computer system you'd give it a piece of information and it goes through its logic gates and it gives you an answer, gives you an output. So it's input, output, and to change the output, software engineering is all about developers recoding and just re-architecting the system. So Watson doesn't do that. So what that ticker was indicating,
percentage.
Yeah, was a probability. So that was a probability of how certain it thought it was in that being the correct answer. So it's not giving you an answer, it's giving you a probability, which is actually it blurs the line. That's really how our own biological brains process information. That's how our own brains work. We learn to walk through repetition and failure, and then you learn from that. And you know that with 99.9% accuracy, if I spill this water out, my shoes are going to get wet. Our brains don't work in certainties. Our brains work in probabilities. And so what's so powerful about that ticker is they actually, so the probability is constantly learning or self-correcting itself based on new information. So they actually didn't just turn the Watson system on and let it play Jeopardy. It actually had to train for about a week to learn how to answer the question. So you may have seen the Watson system answer that same question at the beginning of the week. Car may have been the top choice, but it learns in real time. So basically, what that means is there's no developer, there's no coder, redesigning the Watson system. It's an autonomous self-learning brain, basically. And this has I mean, we're just at the baby step, infancy beginnings of where this is going. So one application area where they've deployed the Watson system is in healthcare. So IBM partnered with Sloan Kettering, a cancer research center in New York, where Watson essentially read all of the latest research in oncology and cancer. It took about a year and a half. So you could think of, I mean, Watson essentially went to medical school. So for a year and a half, read, downloaded all the latest research. And there's more new research. There's emerging research in these cancers that are coming online more than any human physician can keep up with. And so the Watson system today is now more accurate in diagnosing certain types of cancer that are really nuanced and hard to keep track of than a human physician. Probably the most famous at this point that everyone's excited about is in lung cancer. So a human physician diagnoses lung cancer accurately about between 40 and 60% of the time. Watson now is up to about 95, 98% accurate in diagnosing certain patients. So where is this going? This is a headline literally from last week. So I pulled this, and this really blew my mind. So what is the future of this machine learning, and where can this go? Any kind of nuanced decision-making system. So for 100 years, scientists have been trying to answer the question of why, I don't know why they were spending so much time on it, an important question, but when you cut the tail of a worm off, it grows back. They wanted to understand how it regenerated. And it's been like puzzling scientists for over a century. They couldn't do it, couldn't figure it out. So they basically plugged in the data, they gave the outcome, the goal to the computer, and they said, here, work on this. So basically what a computer did is on its own, developed its own theory, developed its own hypotheses, tested its own hypothesis, and came up with the answer. It took it 3 days. No grad students poring over research, no undergrads, poring through data. We now have a breakthrough scientific discovery credited to a computer system. So any kind of nuanced decision-making system, I'll mention I was having